Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to go over a problem in which you're given the equilibrium constant and some beginning conditions, and you're asked to find the concentration of D in a particular reaction. So let's get into this. Okay, so in this problem, we're told determine the equilibrium concentration of D from the following initial concentrations. They give us four sets of different initial concentrations, and we have the balanced equation for this reaction that involves A, B, C, and D. So 2A gas reacts with B gas in equilibrium with forming 3C gas and D gas. And so we're going to use our conditions, we're going to use our equilibrium constant, and we're going to find out D in all these cases. Now, the thing you got to remember is that you have to decide, is the x going to be small? Is it going to shift a lot, or is it going to shift a little? Do you have to do a stoichiometry problem first before you do equilibrium, or can you jump into the equilibrium problem? So I'll be talking a lot about that in this video. Okay, so let's talk about A. So in A, we're given 6 moles of A and 6 moles of B, and the volume of the flask is 1 liter. So in this case, we can go ahead and do our ice table. The reason is because if you look at the K value here, this is KC or KP, KC. So here, the KC here is 6.801 times 10 to the negative 6, and that's a very small K value compared to the concentration we're starting with. So let's go ahead and calculate the concentration. Because the concentration is moles per liter, we got 1 liter for the flask. So if we write the concentration, it'd be 6 moles of A over 1.0, let's make this 6.0 moles of A, 1 mole, 1.0 mole, liters. So this is also equal to the concentration of B, because we have 6 moles of B and, again, 1 liter of the container. So that's going to give us, as can be seen, 6.0 molar. So the moles and the molarity of the concentration can be used exactly the same because the liters is 1. So the other thing is, if we set this up, let's set up our initial part of the table. So for A, we have 6 molar, and for B, we also have 6 molar. So let's put that in for A and B. So we have 6.0, 6.0. And so we're going to start off with 0 here and 0 here. Now, coming back to the equilibrium constant, it's a small equilibrium constant. And so if we write down, again, the equilibrium constant expression for this reaction, it's going to be the concentration of the products over the concentration of the reactants raised to the power of the coefficient. So here we're going to have the concentration of C raised to the power of 3 multiplied by the concentration of D raised to the power of 1 over the concentration of A raised to the power of 2, and then that multiplied by the concentration of B raised to the power of 1. So notice that because this is a very small equilibrium constant, that tells us that the denominator is very, very large and the numerator is very, very small, meaning that the reactants are favored. So at equilibrium, you're going to have a very large amount of the reactants compared to the products. So that tells us that the shift in this direction, we know it's going to shift in this direction because we have 0 products. So it's got to fill in some of the product. But the shift is going to be very small because it really favors this side. So we know we can do an ice table. We don't have to do a stoichiometry first. So let's go ahead and complete our ice table here. Okay, so we know that we're going to lose an X amount here. So because that's a 2 and this is a 1, we're going to have to use stoichiometric amounts. So this is a 2-to-1 ratio. So that means we're going to lose a 2x amount here, and we're going to lose an x amount there. This is a 3-to-1 ratio. And so if we're going to lose an x amount here, so 1 to 3, that means we're going to gain a 3x amount there, and then we're going to gain a 1x amount here. So we're going to just put x there. We add this together, we get 6.0 minus 2x for A, the concentration of A at equilibrium. We get 6.0 minus x for the concentration of B at equilibrium. And then this is going to be just 3x for the concentration of C at equilibrium. And this is going to be x for the concentration of D at equilibrium. So we're asked to find the concentration of D, so what we need to do is find x in each of these cases, and x is going to be the concentration of D. So in this case, we just plug the expression, the equilibrium expressions in terms of x. We're going to put that into our expression here. So I'm going to use the space below here. So let's go ahead and do that. So here we got k is equal to, we got c cubed on top. So that's c right here. So that's going to be 3x cubed multiplied by the concentration of D, which is x, divided by the concentration of A squared, which is this right here. So we're going to have 6 minus 0, or 6.0 minus 2x multiplied by the concentration of B. Oh, I forgot, this is squared because that's squared there. And that's because of the coefficient in front of A. And then B is just 6 minus 0 minus x. And so now all we need to do is solve this for x. Now, we can assume that the x value, I should say, or the change is going to be negligible, because if we look at the k value here, k is much smaller than the molarity that we have to start with. So we're starting with 6 moles and 6 molar. So this is much smaller than this. So we can assume that the change in x here is going to be very, very small. So we can go ahead and cancel out the x, because the loss of x here from 6.0 is going to be so small that our equilibrium concentration for B and A are going to be the same, or very, very, very close to the same. So we can get rid of the 2x here, because subtracting 2x is not really going to have an effect on 6.0. We can get rid of the x, because subtracting x here is not going to have much of an effect on 6.0. And so now it's become simplified that we can solve this pretty easily. So 3x cubed is going to be 27x cubed times x over, and then we're going to have 6.0 squared times 6.0. And then x, so 27x cubed multiplied by x is going to be 27x to the fourth over 6 times 6 is 36. And then we multiply 36 times 6, and we get whatever that number is. So let me calculate that. 216. So we have 216 on the bottom. And so now this is equal to k, which is 6.801 times 10 to the negative 6. So we'll go ahead and put that in. So we have 6.801 times 10 to the negative 6. And now all we have to do is multiply by both sides by 216, divide by 27 both sides, and then take the quad root of both sides, and then we'll get x. And in this case, x is going to be equal to 3.036 times 10 to the negative 2 molar. And so, since we now found x, you'll see that x is much smaller than the original concentration. So, and if you do the 5% rule, we'll find that that's definitely less than 5% error here. And so, since x is the concentration of D, this is our concentration at equilibrium for D. So that is the answer for part A. What about part D? So let's go ahead and do part D, or I'm sorry, part B. Okay, so we're going to set everything up the same way, but this time we are starting with different moles and different volume. Okay, so here now we have 3.0 moles of A and 3.0 moles of B. Okay, and so and we have 2 liters of the volume in the flask. So now we have to use the moles and the volume to find the molarity, because remember, when you're doing an ice table, you have to have molarity. And again, because we're starting with moles of A and moles of B, those are the reactants. Remember, because our K value, or equilibrium constant, is so small compared to the starting amount of reactant, we are going to go in this direction, and it's going to be a small change. So in this case, we're going to do an ice table again. We don't have to do stoichiometry because the K value here supports the reactants, and we have the reactants. We're starting with a certain amount of reactants and no product. So the shift in this direction is going to be very, very small, and so we can do the equilibrium problem. So let's go ahead and do that. But let's calculate the molarity of our A and B, because again, when you do an equilibrium ice table, you have to have concentration. So here, we'll go ahead and erase this. So they got the same number of moles again, so the concentration of A and the concentration of B are going to be the same again. So here we'll have, what do we have? 3.0 moles of A divided by 2.0 liters. And so that's going to be equal to 1.5 molar. So both A and B are going to be 1.5 molar. Okay. So here we have 1.500 again. And so just like in the previous set of conditions, it's going to shift in this direction a little bit. We can assume that x is small. So let's go ahead and set this up. So the change here again is going to be a minus 2x because we're moving in that direction. And the ratio is 2 to 1. So here we're going to lose an x amount. Here we're going to gain 3x again. So that's a positive 3x, and we're going to add here an x amount. And so again, we're going to get our expressions, our equilibrium concentration expressions in terms of x. So we got 1.5 minus 2x. Here we have 1.5 minus x. Here we have 3x again. Here we have x. And now we're going to put these expressions into our k expression here. And so let's go ahead and do that. So we have k is equal to, again, c cubed, the concentration of c cubed. So we have 3x cubed multiplied by the concentration of D, which is x again. So we're going to multiply by D. And then we're going to divide by A. Excuse me. So we got A squared. So here's A. So we have 1.5 minus 2x squared. And then we're going to divide by B, which is right here. So that's going to be 1.5 minus x. And so now we have our expression for k in terms of x. So now we can work to simplify this. We can assume that x is small again for the same reasons as we mentioned before, that the k value here is very small compared to the molarity and concentration of our reactants. So, and that indicates, this indicates that this k value, the small k value, indicates that the reactants are highly favored. So very little of the reactants is going to make product. So very little product is going to be made at equilibrium. So we can assume that x is going to be small here. So we can get rid of the x there and the x there, since subtracting these is not really going to make any difference on those. So the initial concentration is, the equilibrium concentration is assumed to be the same as the initial concentration. So now we can again simplify this. So 3 cubed is 27. That's going to be x cubed times x is x to the 4th. So we're going to get 27x to the 4th over, and this is going to be 1.5 squared, right? 1.5 squared times 1.5, and that's going to give us, what is that? That's going to be 3.375. Oh, by the way, I made a mistake on the previous, well, I didn't make a mistake. I just wrote down the wrong answer that I had written down for part A. So just FYI, the answer that I wrote down was not the correct answer for part A. That was a different part. So just go back. So the answer, and hopefully you figured this out at home when you're calculating it out along with me, you would probably have realized, wait a minute, that's not the answer I got. So the answer should have been 8.58. So for part A, right, I'll write it over here. So for part A, the answer you should have gotten was 8.58 times 10 to the negative 2. Is that right? 8.58 times 10 to the negative 2. That is correct. 8.58 times 10 to the negative 2. So that was the answer you should have gotten for A. That is the answer I got, but I wrote it down wrong from my note sheet that I have. So sorry about that if that confused you. Okay, back to this problem here. So this is going to be on the bottom 3.3, what did I calculate? 3.375, 3.375. And again, this is going to be equal to K, so 6.801 times 10 to the negative 6. So now all I need to do is multiply both sides by 3.375, divide by 27, and then take the quad root of the, or the fourth root, or whatever they call it, of each side. And when you do that, you get x is equal to, now you get that answer I got before. So for part B, you get 3.036 times 10 to the negative 2. Let me double check that. 3.036 times 10 to the negative 2. Yes, okay. So that is the answer for part B. Sorry, I wrote this down for part A. It was supposed to be for part B. That's part A's answer. So let me go ahead and put that in. So that's part B. So this is the answer for part B. Okay, so now let's go ahead and do part C. So give me a moment while I erase the board. I'll be right back. Okay, let's do part C. So we're given 6 moles of C and 6 moles of D in 2-liter flask. So let's calculate the concentration of those. That'll be the initial concentrations. So I'll use this space here. So we got 6 moles. So 6.0 moles of A. Divide that by 2.0 liters. And that's going to give you 3.0 molar. Since both A and B have the same number of moles and the flask volume is the same, so therefore they're going to have the same concentrations. Okay, let's put that into our table and see what we need to do. So here, our initial concentration, as we just calculated, is 3.0 molar and 3.0 molar. Let me fix this. Okay, and oops, C and D. That was C and D. My bad. So it should be over here. So this is going to be 3.0 molar, 3.0 molar. So we've got C and D. We calculated the molarity of C and D to be 3.0 molar for both. That means that we're starting with 0 amount of A and B. And so now we know that it's going to go in this direction because we have 0 reactants, and it's going to shift in the direction to make reactants. Okay, now we got to pay attention to our K value, right? So here our K value is really small, and as I said earlier, that indicates that the equilibrium for this reaction favors very heavily reactants. So when it shifts in this direction, it's not going to be a small shift. It's going to be a huge shift in that direction because it pretty much favors the reactants completely, right? Not quite completely, but enough that what we're going to have to do first is a stoichiometry problem. So we're going to have to do an IF or ICF table first, make sure that we have the stoichiometric amounts, and then go from there, right? So we're going to treat this like a, a limiting reagent problem, and we're going to do stoichiometry first. So therefore, we're not going to use concentration, but we're going to have to use the moles that they gave us. So you use moles in your table when you're doing the stoichiometry first. So what we're going to do is we're going to assume that all of this goes to completion this way, and we do the stoichiometry first, figure out what we have at the end, and then go from there. So let's go ahead and do that. So instead of the molarity, we'll do the molarity a little bit later, but not right now. So we got 6 moles, so we're going to do 6.0 moles here, 6.0 moles here. We're going to assume that it completely reacts in that direction. So this is a 1:3 ratio. So we have to figure out which one of these is going to run out first, which one's the limiting reagent. So here, if I have 6 moles of D, right, and for every mole of D, I need 3 moles of C, then that means that I would, in order to react completely with all of the D, I would need 18 moles of C, because 3 times 6 is 18. So in order for me to have enough C to react with 6 moles of D, I need 18 moles. But I don't have 18 moles. I have only 6 moles. So I don't have enough C to react completely with D, with 6 moles of D. So therefore, I'm going to run out of C first. So that's my limiting reagent here. So this is going, I'm going to lose 6 moles. I'm going to lose all of this. This is going to run out. So I'm going to, for my change here, I'm going to minus 6.0 moles, right? And since this is a 3:1 ratio, if I lose 6 moles of C, then I'm going to lose 1/3 of that in D. So 1/3 of 6 is going to be 2. So I'm going to lose 2 moles of D. Okay? And then if I go over here, I'm going to gain over here, since this is a 3:1 ratio, if I lose 6 moles here, then I'm going to gain 2 moles of B. And again, this is a 1:1, so if I lose 2 moles here, then I gain 2 moles here. And then this is a 1:2, so whatever I gain here, I'm going to gain double that amount. So I'm going to gain 4 moles here. So then that, the final, this is F, final. So the final number of moles that I have after this complete reaction is going to be 4.0 moles of A, 2.0 moles of B. I have 0 left, so I started with 6, I lost 6, so I'm going to have 0 left of C. And then I lost 2 moles of D, so I'm going to end up with 4.0 moles of D. So now I have the final amounts after a complete reaction in this direction. Now that I have that part done, the stoichiometry part, now I can do the equilibrium part and do an ice table. So now what I want to do is take the moles and convert that to concentrations. So here, since in part C I have 2-liter volume flask, so I'm going to have to divide each of the moles by 2 liters to get the molarity. So if I divide this by 2.0 liters, then that's going to give me 2.0 molar. If I divide this by 2.0 liters, that's going to be 1.0 molar. That's 0. If I divide this by 2.0 liters, then again, that's going to be 2.0 molar. So now that I have everything in molarity, I can go back to my table here, and I'm going to do an ice table now. So let's change this up a little bit. So I'm going to erase the initial and replace this with the concentrations that I just calculated. So I'm going to start with 2.0 molar of A, 1.0 molar of B, 0 of C, and 2.0 molar of D. Okay, so everything else I can now erase. And I can do my ice table just like I did before, and we can calculate what the concentration of D is going to be. So again, now since I have 0 concentration of C, it's going to shift in this direction to make C. And so my X is going to be small because again it favors the reactant side. So once again, we're going to lose a 2X amount here. We're going to lose an X amount there. We're going to gain a 3X amount there. And we're going to gain an X amount there. So now we can add these together. So this is going to be 2.0 minus 2X. This is going to be 1.0 minus X. This is just going to be 3X. And this is going to be 2.0 plus X. So now that I have my equilibrium concentrations in terms of X, I can now plug this into my K expression. And let's remind ourselves that what the K expression was. The K expression was K is equal to the concentration of C cubed multiplied by the concentration of D over the concentration of A squared multiplied on the bottom by the concentration of B. So now I can plug these expressions in for A, B, C, and D. So let's go ahead and do that. So here, K is going to be equal to the concentration of a C cubed. So it's going to be 3X cubed multiplied by the concentration of D, which is going to be 2.0 minus, or no, plus X, divided by the concentration of A squared. So here we're going to have, I should probably not have these in square brackets. They should be in parentheses. Let me change that. So we're going to put in 2.0 minus 2x squared, and then we're going to multiply by b, which is 1.0 minus x. Okay, so now that we have our expression here, again, because it's shifting in this direction and our k value is small, it's going to be a very tiny shift, so we can assume that x is going to be negligible. So subtracting or adding x to these numbers is not really going to change the numbers. So the initial concentration or the equilibrium concentration for these values will be the same as, or very, very close to the initial concentrations. So we can go ahead and ignore this, this, and this, since subtracting or adding x or 2x is not really going to change those numbers. So now, once again, 3x cubed is going to be equal to 27x cubed. That's going to be multiplied by 2.0. And we're going to divide by 2.0 squared. But 2.0 squared is 4.0. So we're going to have 4.0 there. And then this is going to be 1. So now all we have to do, okay, remember this is equal to the k value, 6.801. So 6.801 times 10 to the negative 6. So now all I need to do is solve for x pretty easily. So multiply, divide, take the cube root, and when you do that, you get x is equal to, what did I get? 2.00795, which if you round to 2 sig figs is going to be 2. So basically the concentration of D is going to be 2.0 molar. Oops. 2.0 molar. So, which makes sense because we assumed x was going to be small, and when you subtract x, you get a number close. Or when you add x, you get a number that's really small. So here is the concentration. So next, let's look at, and by the way, you could have guessed that D, the concentration of D, was going to be 2.0 based on what I had said just a moment ago, because we said that x was going to be negligible, and if we assume that x is negligible because of the smallness of your K value compared to the starting concentration, it makes sense that your initial concentration is going to be the same as your equilibrium concentration. And so that's what we calculated. Okay, next let's go ahead and finally do part D. Okay, let's go ahead and start D. So D is a little interesting insofar as you'll notice they gave us mole amounts of A, B, C, and D. They gave us 2.0 moles of A, 1.0 moles of B, 3.0 moles of C, and 1.0 moles of D in a 2-liter flask. So we don't know which way, just by looking at this, that it's going to shift one way or the other, right? So if I write down the moles, right, where is it? So we have 2 moles of A, 1.0 moles of B, 3.0 moles of C, and 1.0 moles of D. There's no 0 here, right? Before, in the previous problems, because you had 0 somewhere, that would indicate that it's got to shift in that direction to fill in the 0. But here, there's no 0 amount, so you can't intuitively indicate like which way it's going to shift. So in this case, you have to do your reaction quotient Q. Remember, the difference between your K and Q is that K is specifically defined in terms of equilibrium concentrations. So whatever the concentrations are at equilibrium, those are the concentrations you put into the formula to calculate K. Q is the exact same formula here, the exact same ratios, C cubed multiplied by D divided by A cubed divided by B. Q is the same, but you're putting in non-equilibrium concentrations, so concentrations that aren't necessarily at equilibrium, and then you compare your Q value to K and see how close you are to the equilibrium constant. So let's go ahead and calculate Q. So I'll use this space here. So Q is going to be equal to the same formula. So it's going to be C cubed. So C, we have 3 moles. Now, for calculation of Q, we need molarity because we need to put concentrations in. So let's go ahead and divide by the volume, which is 2 liters. So if we divide this by 2 liters, that's going to be 1.0 molar. If we divide this by 2 liters, that's going to be 0.5 molar. we divide this by 2 liters, that's going to be 1.5 molar. And then if we divide this by 2 liters, that's going to be, again, 0.5 molar. And again, just to recap, I took the moles that were given, divided by the volume that was given, and that gave us concentrations. So now I can put the concentrations in, right? So then Q is going to be equal to the concentration of C, which is 1.5 molar. And that's going to be cubed, right, because we have the cube there. And then we're going to multiply by the concentration of D, which is 0.5. We're going to divide by the concentration of A, which is 1, and that's squared. And then we're going to divide by the concentration of B, which is again 0.5. And now we can calculate the Q value. Okay, and so you can notice here that we have 0.5 on the bottom, 0.5 on the top, so that'll cancel out. We have 1 on the bottom, 1 squared is 1, so this ends up being 1.5 cubed. So all we have to do is take the cube of 1.5 and we get 3.375. 3.375. Once again, so we have our reaction quotient. We're going to compare that to K, and you'll notice that Q is much, much bigger than the K, or you can see that K is much, much smaller than Q. So this tells us that we have much, much more products than expected at equilibrium. So that means that because this is so much bigger than our K value, we can assume that the reaction as it is right now is going to go pretty much to completion in that direction. So we have to do a stoichiometry ICF table, excuse me, or IF table first. So we're going to have to do the stoichiometry in moles first, and then from there do an ICE table just like we did for part C. So let's get ready for that. Okay, so I have redone this, so we're back to moles again, because remember when you're doing the stoichiometry, you do it in moles. And we're going to assume 100% completion in this side, so we're going to figure out what the limiting reagent is. And you'll notice here that we have a 1:3 ratio here, and we have a 1:3 ratio here, which means that both of these will react in completion because they're in the same ratio as the balanced equation. And so that means that there is no limiting reagent, they're just going to completely react together. And so we can go ahead and figure out what the change is. Okay, so here we're going to lose 1.0 moles of D, and since it's a 1:3 ratio, that means we're going to lose 3 moles of C. And since this is again a 1:1 here, so if we lose a mole here, we're going to gain a mole there. And since this is a 1:2 ratio, if we gain a mole here, then we're going to gain 2 moles here. So we got 2.0 moles there. So now we add this together, we're going to end up with 4.0 moles of A after it's done. We're going to end up with 2.0 moles here, and then we're going to have 0 and 0 left of our products. So now we can go ahead and figure out what the concentration is using the liters of the flask, the volume of the flask. So we can now divide this by 2 liters, divide this by 2 liters, and here we're going to get 2.0 molar for A and 1.0 molar for B. So now we can go ahead and do our equilibrium table or ice table to figure out what the concentration of D is going to be. So now we can go ahead and erase this, and we're going to put 2.0 molar here, 1.0 molar here, and this is going to be 0 and 0. Oops, I forgot. I did the ICF table first, and now I'm going to do the ice table. So sorry about that. I forgot to change that to an F. Okay, so now I have this all ready to go for the equilibrium concentration equilibrium table. So now, just as before, this is going to lose a 2x amount. This is going to lose an x amount. This is going to gain 3x amount, and this is going to gain an x amount. And if we add these together, this is going to be 2.0 molar minus 2x. This is going to be 1.0 molar minus x. This is going to be 3x, and this is going to be x. And so now we can set up our K expression like we did before. So let's go ahead and go down here. So we're going to have K is equal to C, the concentration of C cubed. So that's going to be 3x cubed again, multiplied by D, which is x, divided by A, which is squared. So 2.0 minus 2x squared. And then we're going to multiply that by the concentration of B, which is 1.0 minus x. And once again, we can assume that x is negligible for the same reasons before. So we can get rid of 2x and x. So then we can simplify this. So 3 cubed is 27, x cubed is x cubed. And then multiplied by x, that's going to be x to the 4. So we're going to have 27x to the 4th power. And then this is going to be 2 squared, which is 4. And then we're going to multiply that by 1, which is still 4. So we got 4.0. And again, this is going to be equal to the K value here, which is 6.801 times 10 to the negative 6. So now all I need to do is multiply both sides by 4, divide by 27, take the 4th root, and then I should get x is equal to 0.03168, 0.03168, which means if I write this in scientific notation, it will be 3.2. And I'm going to round this to 2 sig figs, so 0.03168 becomes 0.032. So 3.2 times 10 to the negative 2 molar is going to be the concentration of D, because X is the concentration of D at equilibrium. And so that, ladies and gentlemen, is how you do these sorts of problems. Again, you have to pay attention to what you're given. You got to compare your K value to what you're given to start with, and make sure that you interpret and figure out, does your K value tell you which way is it going to shift, and if that shift is going to be a large shift or if it's going to be a tiny shift, right? So remember, your K value tells you what side is favored. Is the reactant side favored or the product side favored? And then look at what you're given to start with and figure out which direction you're going to shift. And then you can figure out whether it's a large shift or a big shift or a small shift. If it's going to be a tiny shift, then you know you can do an ice table right away. If it's a large shift right away, then you can assume 100% in that direction. Do your stoichiometry table first, your ICF or your IF table first in moles, and then from there, figure out what your initial concentrations are going to be for your ice table that you're going to do next. So I hope this helped you with these sorts of problems. If they helped you, if this video helped you, if you enjoyed the video, then please, by all means, like the video, share the video, hit that like button. Also, subscribe to my channel, hit that notification bell up there. Click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.